Hey, all. Today we're going to be talking about equilibrium. Okay. Now, equilibrium is a special circumstance in chemistry. All right. And basically, the word itself, equilibrium, basically means balance. Technically, it is the exact balance between two processes, one which is the opposite of the other. Now, sometimes you can have what is known as static equilibrium, like when you have perhaps a rock balanced on a pinnacle, or or something like that, where something is in balance. Or you can have a dynamic equilibrium. Now, dynamic equilibriums are when, like this, when you have two processes, two things that are occurring at the same time, but in opposite directions. Okay. Now, with chemical reactions, most chemical reactions go to completion. In other words, they proceed until one or all of the reactants are used up. Think of a candle, all right? You light a candle, the candle will keep on going until either you remove the oxygen by snuffing it or it runs out of wax. But it does go to completion. However, other types of chemical reactions appear to stop before any of the reactants are completely used up. All right. Now, these reactions achieve what is known as chemical equilibrium. Now, this is a dynamic state where the concentrations of the reactants and products remain constant over time as long as the conditions are not changed. All right. And that's what we're going to be talking about today is this concept of chemical equilibrium. I'll give you an example. You have water that can react with carbon monoxide to produce hydrogen gas and carbon dioxide. But when this reaction occurs, it appears to stop part of the way through. All right. And just to give you an example, um, let's say you start off with equal numbers of moles of water and carbon monoxide. That's what's going on over here. Okay. Let's get the pointer on here. That's what's going on over here. You have an equal number of water and carbon monoxide COs. Now they start to react together. Okay. Boom, they start the reaction. And some of the products, in this case, the hydrogen and the carbon dioxide, are formed. Now, the reaction continues as time passes and more reactants are changed to products. But after a while, although time continues to pass, the numbers of reactant to product molecules are the same as they were back here. So the reaction appears to stop. No further changes are seen as time continues. The system has reached equilibrium. Now, to give you this in terms that you may understand, think of chemical equilibrium or any type of dynamic equilibrium to be think of like walking on an escalator, but instead of going in the same direction as the escalator is going, imagine that you're walking down an up escalator, or perhaps you're on a treadmill, right? I'm sure at some point or another, we all have gone up a down escalator or vice versa. Now, when you first get on the escalator, you're going faster up than the escalator is going down. So you are climbing up. But if you were to slow down so that you're walking up at the same rate as the escalator is going down, from the side, it would appear like you haven't moved, that you're staying in the same place. All right. Same thing if you're on a treadmill. If you are going the same speed forward that the treadmill is going backwards, your position remains constant. That's all that's really happening with a chemical equilibrium. The forward reaction is occurring at the same rate as the reverse reaction. All right. So how does this occur? Well, let's say you have up here a high amount of concentration rate for the forward reaction, and it starts to occur. Well, as soon as it starts producing hydrogen and carbon dioxide, they start combining together. They have enough energy, they bump into each other, and they start producing water and carbon monoxide. All right. So as soon as the forward reaction goes, then the reverse reaction occurs, and you start producing the original reactants. And it goes one way, goes the other way, goes one way, and they both start occurring. Now, when it first starts off, all right, this is the key thing. When it first starts off, we know and we've learned in previous units that reaction rates are changed by concentration. The higher the concentration, remember, the more particles there are, the more collisions you're going to have, and therefore the faster the chemical reaction rate. So, as concentration goes up, reaction rate goes up. We learned this. So, as the reactions proceed, the reverse reaction speeds up. Why? Because its reactants are increasing in concentration. All right. In other words, as this is going, we're getting more and more, as the original reaction goes, we're getting more and more hydrogen and carbon dioxide. Since those are the reactants for the reverse reaction, that reaction is increasing in speed. That's why you see it going up there. All right. At the same time, the forward reaction, the water reacting with carbon monoxide, it starts off going fast, right? Because they have a lot of reactants. But as it starts to get used up, it slows down. All right. So the forward reaction starts to slow down. So the forward reaction slows down, the reverse reaction speeds up. And they start to speed up and slow down until they end up going the same rate. All right. So it's kind of like you're going up the down escalator quickly. All right. But you start slowing down and the escalator starts to speed up until you guys are going the same speed. Once the speeds match, that's when it's in equilibrium. So when the reaction rates of the forward and reverse reactions are equal to each other, the reaction has achieved chemical equilibrium. All right. Hopefully this makes sense. All right. Big concept to get here, but it's a very important one. And we're going to see how this concept of dynamic equilibrium works in the activity dynamic equilibrium. But a few things to note about it. First of all, a reaction at equilibrium is indicated by a double yield arrow, either by a single arrow that has two arrowheads on it, or by a reaction arrow like this, where you have one forward and one reverse. For example, what you see here. Now, another thing to keep in mind, and this is something that people don't quite get sometimes, at equilibrium, both the forward and reverse reactions continue to occur. Even though from the outside they look like they've stopped, they haven't. They are still occurring. All right. Just like from the outside, if someone's not watching your feet, it may look like you're standing in the same place when going up a down escalator. But if you can actually see the feet and the escalator, the feet are still going up, the escalator is still going down. It's just from the outside, it looks like it has stopped, but it hasn't. Same thing with a chemical equilibrium. The forward and reverse reactions are still occurring. All right. And something else that people don't quite grasp. Once equilibrium is achieved, the relative amounts of the reactants products are not necessarily equal. Okay? Once it achieved equilibrium, the amount of hydrogen and carbon dioxide doesn't necessarily have to equal the amount of water and carbon monoxide. Thinking that they have to be equal is saying, like, well, the only way that you're going to be able to reach equilibrium going up a down escalator is exactly in the middle, halfway up and halfway down. But that's not true. You could match your speed close to the bottom, all right, and be most of the way down. And that would be like you have a lot of product and very little reactant. Or you could be going fast, fast, fast and get up right to the top and then slow down so that you're right up at the top. All right. That's like saying you have a lot of reactants and very little products. All right. It doesn't necessarily mean that you have to have equal amounts. You could stop in the middle. You could stop near the top. You could stop near the bottom or anywhere in between. The relative amounts are not equal necessarily. Okay. It's the rates, the reaction rates that are equal. And that exact ratio of products to reactants can be calculated mathematically. Now, this is known as the equilibrium position. Now, we're not going to worry about that too much. All right. We're not going to worry about the equilibrium position so much, and we're not going to calculate it mathematically or anything like that. All right. We're just not going to worry about that, but it can be done. What we are going to worry about is, first of all, equilibrium position is the particular set of equilibrium concentrations of all the reactants and products in a chemical system. All right. In other words, where you stop, as it were. Are you close to the bottom, close to the top, somewhere in the middle? That's known as your equilibrium position. We're not going to worry about the exact numbers. What we are going to focus on in the next section here is this concept here. If conditions that affect reaction rates change, then the equilibrium position can also change. Remember back to what changes reaction rates? All right, things like concentration, temperature, surface area, things like that. Well, if any of those change, it's going to change the equilibrium position. It's going to alter how much reactants and products you're going to have. That is important, and that is what we're going to focus on in the next section. All right. So hopefully this helps you. If you have any questions, please come to tutorial. I'd love to help you guys out.